This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus. It's episode 671, and this week we welcome Penn State Professor Dr. B.Bahnfleth, Dr. Dustin Poppendieck of the National Institute of Standards and Technology, and Allison Savage from EPA's Indoor Environments Division. We're here for part two of our series on the National Academy of Science, Engineering, and Medicine's document, Why Indoor Chemistry Matters. This week, we'll focus on the management of chemicals in indoor environments. But before we get started, let's thank our sponsors. They're the reason we can continue during the show. Don't forget after the show to continue the discussion at afterthoughts.iaqradio.com, sponsored by First On Site. Our marquee sponsor is First On Site at firstonsite.com. Our association sponsors are the American Conference of Governmental Industrial Hygienists, ACGIH.org, the American Industrial Hygiene Association, AIHA.org, the Cleaning Industry Research Institute, CIRI Science.org, the Institute for Inspection, Cleaning, and Restoration Certification, IICRC.org. Industry sponsors are AEML Laboratories, AEMLINC.com, Particles Plus, ParticlesPlus.com, TSI Inc., TSI.com, Sunbelt Rentals, SunbeltRentals.com, April Air, April, AIRE.com, Healthy Indoors Magazine, HealthyIndoors.com.
And now you can win a cool prize. It's time for the IAQ Radio Trivia question. Be the first to correctly answer. Simply email your answer to czlotnick@cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man.
Hello, everyone. Here's today's IAQ Radio Trivia question. It's sponsored by TSI Inc., an industry leader in precision instrumentation for monitoring of indoor air. Learn how to expand your IAQ investigations at tsi.com. Here's the question. Name the combination of three words by which hydroxyl radicals were originally called after their discovery. Back to you, Joe.
All right. Thank you, Cliff. Today we've got William Bahnfleth. He's a professor of architectural engineering at Penn State University. He's also the author or co-author of more than 170 technical papers, articles, 14 books and book chapters, and is an ASHRAE Fellow and past president. Dustin Poppendieck is the environmental engineer at the National Institute of Standards and Technology. He's also a fellow of the International Society for Indoor Air Quality and Climate. And Allison Savage is a biologist in the Indoor Environments Division in the Office of Radiation and Indoor Air at the US EPA, and is a current team leader of the scientific analysis team. Welcome, everybody. Great to have you. All right, let's start with introducing our two new guests. I don't think we have not had Dr. Poppendieck or Allison Savage on the show in the past. We're a little bit familiar with NIST because we've had some great shows in the past from with people from NIST. But let's talk a little bit about first with Dr. Poppendieck. How did your position at NIST end up getting you involved with this indoor environmental project, chemistry of indoor environments, I should say?
Sure. So we'll back up a little bit and how I got into indoor air quality in general. And for me, it all started with the anthrax attacks of 2001. And we had postal office buildings and the Senate Hart building were contaminated with anthrax. And we knew how much disinfectant we needed to disinfect to basically kill the spores in a lab space. But when they went to dump all this disinfectant into these various buildings, they could never reach the doses they were trying to do. And so my first project was to actually figure out why we weren't reaching those doses. And we basically tested everything to figure out that the disinfectant was being consumed by the surfaces in those buildings. And so basically we quantified and modeled the reactions to try and start understanding that chemistry was happening in indoor environments. And that was my first leap into indoors. After looking at some emissions from kerosene lamps in developing countries, I spent some time looking at methamphetamine remediation from illicit drug manufacturing. And we found that latex paint encapsulation was not actually effective at significantly reducing emission rates. And so that was kind of opened my eyes to, things are migrating indoors. Not only do we have chemistry happening, we have things migrating through materials. And then when I got to NIST, I actually started looking at one of my first projects here was looking at emissions from spray polyurethane foam, and trying to figure out methods to how to quantify the emission rates from those. And basically, it really opened up my eyes to that our indoor environments are really chemical reactors, and SPF was one of these industries that actually enhances that chemistry in our indoor environments. And so we really thought, now we have all these sinks and sources, and it started opening my eyes to all the sinks and sources that we have indoors. After looking at some emissions from distinguished cigarette butts, we went on to, we modeled some emissions of flame retardants in our net zero house here at NIST. And that really got me into thinking about partitioning and how you can partition from materials to particles and air, and how the interaction of all those things play together. And then to really answer your question, how I came into this is via Charlie Westerlo, who I've known for over 20 years. He was actually involved in that first anthrax project, but he came to NIST 3 or 4 years ago and toured our net zero house and said, this would be a wonderful test facility for some indoor chemistry experiments. And so he contacted Mariana Vance and Delphine Farmer, who led the home chem studies, and they decided to do the chemical assessment of surface and air experiments, a series of 2 months of experiments with 12 different universities here at NIST this spring. And we looked at how indoor chemistry affects smoke aging and cooking partitioning into cooking particles, how surfaces age as you add those types of contaminants, and then also looking at the indoor and outdoor migration of chemicals. And so that basically got me to the conclusion that indoor chemistry is really complex.
Very complex. That's a really great introduction to you and what you do. And I before the show, I had asked you already, we'd love to get a show with just you and maybe go into some more detail on some of those projects. The spray foam is one that I know a lot of our listeners are very interested in. And I look forward to doing that in the future. But before we do that, let's finish this chemistry of indoor environments here. This is interesting. Allison, I'm curious, you've worked on quite a few interesting projects at EPA yourself. How did this one make you look at your own indoor environment? Did it change your thoughts at all?
Thanks for the question, Joe, and thanks for having me today. We were really thinking about indoor chemistry well before this report and this project started. But since I started getting into indoor air quality and learning more about indoor chemistry, there were definitely a few things that stood out to me. One was that the use of some of these consumer products can, in the right circumstances, result in the formation of new particles. And I think that's something that I hadn't really thought about a lot before learning more about indoor air quality, and I don't think a lot of people realize yet, that that's happening. Another thing that stands out to me, at the Indoor Environments Division at EPA, we develop a lot of guidance and provide technical assistance to the public for mitigating a lot of different indoor air quality issues. And there are a lot of different strategies, and there's a lot of complexity, as Dustin pointed out, in indoor chemistry. And I think for people who aren't thinking about this every day, it can be a lot to take in at one time. And so, we can try to boil down how to mitigate certain indoor chemical hazards into a few key principles or strategies. But as the report that we're discussing today points out, clear communication about indoor environmental mitigation approaches, and particularly approaches for air cleaning, will be really important moving forward. And the work that the committee did on this report will really lay the foundation for that, for us to do that in the future, and for future research that'll help us clarify some of our public health messaging at EPA.
And I also talked to you before the show about, maybe doing a little something in more detail, especially on that recent, I guess it was a website update. Can you tell listeners a little bit about that project on the flooding?
Yeah, Yeah, sure. EPA recently put up a new website on cleanup of flooded homes. It's got a series of how-to videos. It's really aimed at people who are impacted by widespread flooding, where there might not be a lot of resources to go around in terms of, professionals to help with cleanup or technical assistance. And so these videos show people kind of step-by-step how to do some of the things they'll need to do if they're affected by a widespread flood, a hurricane, or something like that. It also has some neat infographics about the different hazards they might encounter and how they can sort things that can be kept or restored and some things that can't. And so it's a really great new resource. There's a lot of interesting stuff on there. And so I definitely encourage people to check it out. It's epa.gov/flooded-homes.
And we will put that in the blog and make sure we get it out. And I look forward to talking to you and maybe some of the other folks that worked on that in the future. All right, Bill, let's go over to Dr. Bahnfleth. Bill, you're one of our favorite guests. We love having you and always appreciate you joining us. I understand you did a little research or a little checking into the document on this whole partitioning thing. All right, why don't we start there with figure 3.2, John, if you would, and kind of just review for our listeners what partitioning is and how it would relate to the type of work a lot of our people do with respect to inspection and remediation of indoor environments.
So did you want me to answer that or Bill? You originally had said me.
Well, why don't you both touch on that?
Yeah,
let's start with you, Dustin.
I think Dustin probably has a more fundamental understanding of this than I do. So,
all right, let's do that.
Yeah.
Okay, I actually have I think a decent answer on this one. So otherwise, I'll step on your feet, Bill. So partitioning fundamentally is really just accounting and keeping track of where chemicals are. And a really good way to think about this is thinking about going to a beach on a sunny day. And you have a bunch of people who are on the beach and you have a bunch of people who are in the water. And the ratio of the people who are on the sand to the ratio of the people who are in the water is basically just a partitioning. It's a partitioning of people in the water versus people in the sand. And that can be thought of a partitioning coefficient. It's important to remember that when we're talking about partitioning, we're not talking about kinetics or the rate at which things happen. So we're not talking about how fast those people are going in and out of the water. We're just talking about how many are in the water versus how many are on the beach. On the sand. But the partitioning coefficient is really dependent upon a lot of factors, the environmental, the chemical, and the material of that we're thinking about. So if you're thinking about in a beach scenario, if it's really cold water, most people are going to be on the sand. If it's raining, a lot of, there's not going to be many people on the sand, but you might still have some few people surfing. And so partition coefficients like that are very dependent upon our indoor temperature, our relative humidity, in the same manner that chemicals, the ratio of the chemicals are going to be in the surface and the air. The partitioning coefficient is also going to be very dependent upon the chemical. Say if we take all the people on the beach and the water and we replace them with whales, we're going to have a very different ratio. Every once in a while we'll get a whale on the beach, but generally most of it's going to be in the water. Likewise, if we replace the whales with deer, we're going to get most of them on the beach and very few in the water. And so it's very chemical dependent for, in addition to environmentally dependent. And then the material is also going to impact the partitioning coefficient. So if say we had a rocky beach instead of a sandy beach, we'd have far few people. We have a different ratio than we would otherwise. So the materials that we have are going to very greatly depend upon it. And then if we start thinking about the big picture, we need to think about the capacity. So if we take, for instance, the state of Florida, where we have lots and lots of beaches and lots of people are going into the water, they're going to impact, we'll have more people in the total in the water. Whereas we look at maybe the state of Alaska, where we have very few people going into the water because of the temperature. So the amount of the capacity of our material to absorb that thing is also going to be important when we start talking about partitioning. And so if we go to the indoor environment instead of our fun beach environment, we need to remember that the chemical is going to partition to everything. And that's really what this figure is about, is that, our air is providing the medium of which to distribute the chemical throughout all these different media, whether it be, the gas, whether it be the particles, you have dust, whether it's the solids, that be wallboard, flooring, insulation, couches, cabinets, even liquids like toilets that can have water, which will have partitioning into them. And so basically partitioning is going to kind of control how things happen. And we're not always going to be reaching what we determine our partitioning, because partitioning is an equilibrium condition. And the indoor surfaces are really dynamic. They're changing over time. They're getting cleaned. They're getting refurbished. They're repainted. And so the surfaces are going to be different over time. And in fact, we can get into this later on how they build up organic films and things on that. But overall, it's what we're gearing towards, that ratio of what's in one media versus another media. And in most of when we're talking the indoor environment, it's the ratio of the air to the ratio of the material.
Yeah, I would just add to that. Well, first of all, to go with your analogy, we're often concerned about removing things that are partitioned to the air. And if the ocean is like the air, then, just imagine sharks taking a swimmer every once in a while. Still a lot of people left on the beach. Close the beach and you get rid of whatever it is that we're talking about. And I think that's the practical implication here is that partitioning, as described in this chapter, tells us that by far most of the hazardous chemicals are in solids and on surfaces and not in the air. And yet our methods of control generally have to do with trying to flush things out of the air. And even if you ventilate to a very high level, still a lot of stuff left there, and you stop ventilating and it's going to come back. And I think that's a very important practical consideration that points to the need for surface cleaning and sometimes for replacing materials as well.
And I think that's a great point. A lot of our listener base, they deal with wildfire smoke, which we talked a little bit about before the show, and other types of fire-related damage. And I can just imagine, you clear the air out, but then you still have all that soot that remains behind and is on surfaces and so on and so forth. And even though you cleared the air out, you close the building up, and that odor comes right back again. And so you've got to do something about both. Go ahead, Bill.
The third-hand smoke issue that was discussed. Tobacco, but it could also be wildfire smoke.
Yeah, I think it also illustrates how complex indoor environments are. I think what we'd like to do, John, let's go to that next figure, 3.3. I thought this was interesting. It's a little different way of looking at indoor environments. Let's put it up and have one or all of you comment on it. How is this important? And again, keeping in mind that, we're dealing with people who inspect and remediate indoor environments. So who wants to take this one?
I can start. I think the big thing here is, we have a wide range of different types of chemicals and materials, and they're all going to partition to different materials differently. But we can have orders of magnitude higher mass of chemicals in these surfaces than we do in the air, especially when we're talking about less volatile chemicals like SVOCs, things that, you might see methamphetamine or PAHs or things like that. You might see these orders of magnitude in these surfaces, and they have partitioned at very low rates, very low concentrations into the air phase. And so when you're partitioning at a very low rate, if you're removing that air and trying to clean that air, whether it be by ventilation or filtration or some other mechanism, it's going to take a very long time to remove that reservoir, because that reservoir can be 100 or even 1,000 times bigger because we have such big volumes. Another important point that we have to think about is where the chemicals are located. So if you have a chemical that was brought in with the material and is distributed throughout the bulk of the material, say, you might have a urea formaldehyde glue that's slowly releasing formaldehyde over time, that formaldehyde has to migrate through that entire material before it releases, but there's a huge amount of it. Versus if you have, say, a chemical that has been applied recently, say you have a smoke vent, or you have a cooking event or something like that, it'll go to coat the very surface of the material. And so the availability of that reservoir to hold a lot of mass is going to be highly dependent upon where it starts, whether it starts in the bulk of the material or if it starts just in the very surface film because it was introduced through the air.
Yeah, and another thing that's pointed out in this chapter is that the relatively large surface area per unit volume. So the surface area of these reservoirs can be very effective at transferring some of the material that's partitioned to the surfaces and solids into the air.
It was,
I think
yeah,
that was the
we
thing that got
highlighted in
my
the
attention. Go ahead, Dustin.
We highlighted in the report that you get about 3 meters squared for every cubic meter of air. So 3 meters squared of surface area in your indoor environment per every meter in the indoor environment.
And how does the room environment, things like temperature, relative humidity, how does that affect this whole partitioning issue?
It's very important because things can sorb and desorb from surfaces. And I think it's an underappreciated aspect of HVAC design that poor temperature and humidity control can contribute to worse air quality because of that. So that's my short answer. And Dustin wants to add something more scientific here.
So in general, temperature is going to drive the increase emission. The rule of thumb is roughly every 10 degrees Celsius increase is going to double your emission rates. But relative humidity is more interesting because when water vapor starts to coat a surface, it can form a variety of different of things. It can form a puddle, an aqueous film that you could actually visualize as a little puddle on the surface, or just a few water molecules layered together. And those all have very different chemical properties, whether it's what you would think of a water or just a few water molecules. And then when they start going on that surface, if you have a chemical that likes to be in water, relative humidity may decrease the concentration. Increasing relative humidity may decrease the concentration of that chemical in the air. Or if you have a chemical that doesn't like to be in water, say benzene, that something with an aromatic structure, that's going to start to emit at greater amounts because it's getting pushed off the surface by the water. And so those might increase with concentration with relative humidity. So relative humidity can be very chemical dependent on what you're going to see in the indoor environment as far as concentrations.
I've got a couple text questions. One is how do airflow patterns in a space affect the partition coefficient?
That's a good question, in that the partition coefficient is an equilibrium parameter. It's not measuring the mass transfer. And so it's a parameter that says when everything is at equilibrium and we don't have any changes, this is the ratio I'm going to see between the air and the material I'm interested in. Now, if I change the flow over that surface, that's going to change the rate at which it's going to want to partition, but it's not going to change the relative ratio at which it wants to be at. So the partition coefficient doesn't change, but the mass transfer values certainly will change depending upon the airflow. So
you can make an analogy to heat, right? You turn on a fan to cool yourself. What's it doing? It's removing heat from the surface of your skin, either as latent heat or as sensible heat.
And that heat goes into the air. Okay. And then I've got another one. When you say chemicals, do you mean mostly VOCs, or are you including those chemicals that are also on aerosolized particulates?
Yes, any chemical.
Any chemical. Okay. And
we can have chemicals in indoor environments that have 10 order of magnitudes different vapor pressures or boiling points, however you want to look at it. So they all migrate to various degrees and extents.
All right. Now let's move on to, we've already talked a little bit. Let's talk about chemical transformation and how it infects those of us in the inspection and remediation industry. Who wants to jump in on this one? First, let's talk about what transformation you mean by transformation, and then discuss maybe how it might affect those of us trying to deal with indoor environments.
So chemical transformation is basically any process that leads to the loss or removal of something. And it's important to know that, they can be very different. The process that you change into, the chemical you change into, can be very different from the chemical you started with. They can have very different terms of reaction toxicity and things like that. That's kind of like if you bake and you put a whole bunch of ingredients together to make chocolate chip cookies, you end up with a nice cookie at the end. You don't end up with those other components. And sometimes it's going to be it's not going to be reversible, like with a cookie, but maybe the chocolate chips you could pull out and they might be reversible. And so when we're talking about transformation, it really can happen anywhere. You can have it happen in the gas phase, particle phase, surfaces. I think we're really acknowledging now that surfaces, especially things with large surface areas, HVAC ducts, these are all things that we may be seeing a lot of transformation happening. We can go into the specifics of the drivers, but I'll let Bill or Allison jump in at this point.
Bill, do you want to add anything, or Allison?
I would just say, again, more from the user perspective. I think we don't give enough consideration to the fact that the things that we put into an indoor environment are actually causing chemistry. We tend to just think that we have sources, and if we ventilate or if we filter, we're removing the contaminants, and actually there's a much more complex bunch of processes going on where things are being converted. I don't think that we think about, for example, if I bring in more outdoor air that has more ozone in it, that it increases the ozone chemistry inside, but at the same time it's reducing the amount of time that air spends in the space, and that has implications too. So it's, I tend to think of it as maybe the second order but still important effects that this research is starting to make known, and I think that's an important development.
Allison, did you want to chime? Go ahead.
Yeah, I'll just add, I think, there's certain activities that have maybe more potential for some of this secondary chemistry, like, bringing in more outside air that has more ozone, like Bill mentioned. Cooking can release some compounds that can be kind of drivers of these chemical transformations, cleaning activities with certain types of products too. So, identifying some of those drivers and some of those activities, they're more likely to release some of these, drivers of indoor chemical transformations, can help us kind of target our messaging or target our, what we do to help reduce the potential for some of these transformations that might result in more hazardous products or products we don't necessarily know what that means for toxicity or for health.
There's times when during remediation, we actually intentionally inject things like ozone or hydroxyls, or for instance, Bill, I want to ask you on you do a lot with UV light. What kind of transformations does UV light cause?
Well, certainly photochemistry is well known, and it's been much studied outdoors, mainly for UVA and UVB, because UVC, which we use germicidally, is filtered out by the atmosphere. We can assume that there's chemistry going on with UVC, but it hasn't been very well studied, and I haven't seen evidence to date that anyone's documented a real problem, unless we're producing ozone with lamps, which is avoidable. I found one study when we were putting this report together where someone had actually done experiments using 254 nanometer UVC, which is a germicidal wavelength, with toluene to see whether they could generate secondary organic aerosols, and they did, but with a level of toluene concentration that was at least 10 times the PEL, and with a level of UV irradiance that was probably 10 to 100 times higher than what you would use in these systems. And when they did a test in a more realistic environment, they didn't find that they could measure anything of significance. So my suspicion is that it's not a big problem, but it shouldn't just be waved off. I think we need to do more study of how germicidal wavelengths interact with the materials in buildings particularly.
Dustin, you've done a lot of work. You talked about the anthrax and disinfection. I wonder how much information there is on how applying disinfection products maybe affects this partitioning, or not the partitioning, the transformation.
So I would say, fundamentally, we don't, and I think we highlight this in the report, is that we don't understand the chemistry in the indoor environment. We really don't have a good handle on all the reactions and all the consequences of things that are happening in the indoor environment. We know chemistry is happening. We know it's happening to we can demonstrate, that hydroxyl radicals are going to oxidize both alkenes and hydrocarbons and form peroxyl radicals and all these other complex products and peroxides and carbonyls and carboxylic acids. But as we say in the report, that the health effects, the exposure to those emissions and the chemistry from those are really not well understood. We don't have enough studies that are with standard tests that can give us good data to really quantify the health effects and potential chemistry that's going on. And that's not just, I don't want to focus on hydroxyl radicals or UV. I think that's true across the whole spectrum of air treatment technologies.
Hey, Joe, if I could, I'd like to follow up with Bill. Bill, there's some data that I found in terms of UV reactions. And one was a study that was done by a Canadian manufacturer of UV equipment. And it was reactions with human skin particles and ozone. I'm not sure whether or not you're familiar with it, but
no, I'm not.
I'll send it to you after. But
Yeah,
what they found was that it caused odors, inside these indoor environments. And just one caution, when the lights go in, I think in commercial situations, they're generally always installed properly. I think in these residential systems, they put in UV lights, and there can be some other things going on in that ductwork. There can be plastics that can degrade from UV. There can be rubber. There can be I've seen situations where I've been called to inspect odors, and that's kind of what we've traced it back to. UV light reactions, causing odors after the bulbs were installed, and when the bulbs were taken out, the situations had a tendency to resolve.
Yeah, that's certainly true. As I think most UV installations in HVAC systems are retrofits, and there's some material compatibility issues. Those who are interested, there's an ASHRAE research project on effective 254 nanometer on HVAC related materials that you could look up, and that was very interesting. So the thing I would pick up on in the first example was, I think you said they were actually putting UV on skin and generating.
No.
This was just from the air.
This is just settled skin particles that were in carpets and were in an environment, and this company found that UV reacted with it. I mean, they were actually the manufacturer of the bulbs and so on and so forth.
Were they considering applications that would be like cleaning unoccupied rooms? Because with 254, you just shouldn't be irradiating people with it. You would be using it in a whole room only if it was unoccupied. And I could imagine if you did that at a higher irradiance level than you would normally use for air disinfection, other things could happen. So as I said at the outset, there's no doubt there's chemistry. The question is, under what circumstances is it chemistry that makes a difference?
So one report that we highlighted, or one paper we highlighted in the report, shows that that we have a huge amount of skin cells that we shed every day, and so even if we're not present in the room, once we leave the room, there's still a bunch of skin cells and skin oil that are in the room that can cause that reaction to cause chemistry to happen, even if we're not present. And there's a lot more work on ozone and skin oil, showing that the unsaturated oils that we have in our skin, that double bond is getting broken down by the ozone, and that can lead to a whole bunch of different chemistry that happens as that double bond breaks down, and then leads to a cascade of all these other different chemistries that can happen, and all these other chemicals that can be produced. And it's a pretty fast reaction that actually happens on those things, but that's with ozone, and we see it a lot with the skin oils and ozonolysis, resulting in an array of different aldehydes and ketones, even when those oils are like spread on dirty laundry or a piece of
and that ties into something else that was discussed, which is the importance of of keeping surfaces clean, because settled dust is a reservoir that can put a lot of things into the air. And I'm not going to throw a percentage, but as I recall, house dust is a pretty high percentage skin flakes and dust mite parts, and in my house, cat fur. So yeah, there are organics there that can be acted on by chemicals and by light.
All right, let's stop here for a moment. We want to thank our sponsors for our halftime here. I see I've got a couple of other questions from the audience. We'll try to get to those in the second half, but we're going to focus on the management of these indoor environments and the chemistry of that. So we'll be right back with our guests. Our marquee sponsor is First On Site, your trusted full-service disaster recovery and property restoration company at firstonsite.com. Our association sponsors are ACGIH, Advancing Careers of Professionals in Environmental Health, Industrial Hygiene, and Safety, interested in defining their science. ACGIH.org. AIHA, Healthy Workplaces, A Healthier World. AIHA.org. The Cleaning Industry Research Institute. See more deeply through science and research. CIRI science.org. The IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry, IICRC.org. Industry sponsors are AEML Laboratories, free shipping, great pricing, same-day results with no rush fee, AEMLinc.com. Particles Plus, feature-rich particle counters and air quality instrumentation. Count on us. ParticlesPlus.com. TSI Inc., an industry leader in precision instrumentation for monitoring indoor air. Learn how to expand your IAQ investigations. TSI.com. Sunbelt Rentals, availability, reliability, and ease for all your IAQ and restoration needs at sunbeltrentals.com. April Air, healthy home, April, AIRE.com. And Healthy Indoors Magazine, a free online magazine for industry professionals and consumers, healthyindoors.com. All right, let's just jump right back into it here. I want to talk more about the management of chemicals in indoor environments, and I'm going to tie some of these audience questions in as we go through management because they fit well into this topic here. It's tough enough for a practitioner base to figure out what chemicals are in the indoor environment, but then when they have to think about, are they partitioning and all the different interactions within the indoor environment, it really makes things tough. I wonder if one or all of you would like to comment on why are these importance of partitioning and transformation? Why is that important to our practitioner base?
So I think one of the points that was mentioned earlier, I think Bill talked a bit about this, is that, a lot of our mitigation strategies can be focused a lot on the air reservoir. And when, we're just focused on that one compartment, it might not fully address an issue where a certain species is really hanging out more in some kind of surface reservoir or some kind of bulk material. So I think that's certainly something that's important to understand about partitioning and about transformations. And I think something else about the complexity that this really highlights is the importance of source control and removing things we know or expect might be less than desirable to have in an environment is really important because, if we don't introduce new chemicals unnecessarily, we can also avoid some of these potential unintended consequences that result from partitioning and chemical transformations that are happening that we may not fully understand yet. So using proven mitigation strategies like ventilation or like filtration can really help with avoiding some of those unintended consequences.
I think you bring up a great point, and I think it's important for our base because, a lot of our customers, they look at it as either it's in the air or it's on a surface, not that what's in the air could also affect what's in surfaces and what's on surfaces could also affect what's in the air. So I think it's a complex situation. And part of the issue our people run into is that, they'll flush a building out and maybe do what whatever maybe the insurance company or the customer is willing to pay for with respect to surface cleaning. And then the problem comes back when they leave. And this kind of helps to explain why that happens, I think. So I don't know, Cliff, what do you, anything you'd like to add?
I think from a remediation standpoint, it's more complex than people would think, because number one, you have this background load, then you have the event and everything that happened during the fire, new chemicals are created, so on and so forth. And then you go in, you add different chemistry during remediation, and then following remediation, you start adding coatings, and you repaint, you introduce new building materials, carpets,
New carpet,
so on and so forth. It's
drywall.
It's really complex. And I think that, one of the things we've learned from these shows is that, a lot of these ozone reactions tend to occur more on surfaces, and, a lot of the hydroxyl reactions tend to occur more in air. And, that was enlightening, because I think, we would just go in and do the best we could, and we would listen to what manufacturers told us was going to happen when we put these miracle devices in there, and everything's going to turn to carbon dioxide and water vapor, and that just doesn't always happen.
I think if you go back to Max von Pentecoffer's quote from 1858, that if there's a pile of manure in the space, don't try to remove the odor by ventilation. A pile of manure. I think we have a lot of piles of manure in the indoor environment, and we need to realize that it's a big pile of manure, and just ventilating is not going to get us out of the problems in some cases. And to realize that even if you remove the pile of manure, the barn still smells, and you have all these other materials that smell is going into, and you need to start thinking about reservoirs and thinking of materials as reservoirs. And so what is your biggest reservoir? And so for your specific chemical, for instance, carpet has a foam backing, and that could absorb chemicals very easily. If you have furniture with padding, the polyurethane foam padding, that's a great absorbent that can absorb chemicals very easily. Walls are just a huge surface area compared to the walls, compared to surface area of other materials. So then we have another huge reservoir potentially for chemicals to stick to that we need to think about. And so I think when you start talking about, thinking about partitioning, we're really thinking about reservoirs and how things are getting into those reservoirs. So if you have a really sticky chemical that's not very volatile, you really need to start thinking about all of these reservoirs. If you have something that's pretty volatile, say like acetone or something, it's not going to be in those reservoirs to a very significant extent. In those cases, we can start thinking about air treatment. But if you have an illicit meth house and you're trying to clean it up, let's get rid of the manure. Take up the carpet, remove the wall board, and things like that are going to have it's going to be the only way to really remove those reservoirs for long term.
If I could ask you a question, one of the things that in restoration we've used pretty successfully as a technique and method, when certain odors remained in a surface that had been cleaned, it actually looks pretty clean, but is desorption. And what's been done is going in there with VOCs, in most situations ethanol or isopropyl alcohol, diluting it with water, spraying it onto surfaces while you had really heavy ventilation going on. And that tended to desorb these surfaces. Sometimes it might take more than one treatment, or 3 or 4 treatments, but typically we could notice after each treatment that there was an improvement. And generally, we were able to remove the last vestiges of odors from surfaces that look clean. And I guess because what we were using was more volatile than what remained, and hopefully, I guess this combination of volatile of VOCs to SVOCs or even slower VOCs, might help carry them off. So, do you think it makes any sense, or we shouldn't do it, or any comments?
I would say, going back to the report, indoor chemistry is really complex and really incompletely understood. And so, we have all these things that we're putting into the indoor environment for remediation situations, I would say the vast majority of them we don't understand fully what's happening. And just because we remove an odor doesn't necessarily mean we've reduced the risk to the occupant. It could be that you've transformed that chemical into some other chemical that's now below an odor detection, but that other chemical may be more toxic. And until we have, and one of the real big challenges of the indoor environment is that we have millions and millions of indoor environments that are all different. And so what may be a viable technique in one indoor environment may be completely irresponsible in another indoor environment, just based on all the different contents of those indoor environments. And we really don't have a handle on what's good advice and when to use where, because we just don't fully understand the chemistry, both on the surfaces and in the indoor environment. And I think that's one of the big take-home points from the report is, you can go through any of these technologies, PCO, ionizers, hydroxyl radicals, any of these things, or we just don't fully understand what's going to happen in the lab, let alone in the real world. And, I understand the predicament that we're in, and that, we've got these indoor environments that we're trying to reuse and make habitable, and we've got to try something. But I think the real take home is that we really have to understand that we don't fully understand what's going to happen in the indoor spaces.
But I think that some of those technologies are known to be very reactive. The photocatalytic stuff and ozone and hydroxyls and peroxides and all these other things. And, it seems that some of the things that we use in remediation, a lot of it gets down to soap and water. It's detergents and water. And, I think that, again, yes, we're adding certain chemistry to that, but I think what we're adding has a tendency not to be as reactive as, some of the things, such as, the oxygen species and so on and so forth.
Yeah, I think there's a big difference between someone who's a professional doing a remediation job, being properly protected, knowing how to handle things, and putting some potentially harmful substances into the air that people are breathing all the time, even at low levels. I think that's the kind of question that we haven't answered yet fully, is what kind of chronic exposures are important and to which. And that we always come back in these discussions to the need for an actionable definition of acceptable indoor air quality in terms of what's in the air, and it can't be 10,000 things that we have to control. Somehow we've got to rank the major risks and take effective measures to limit them. Otherwise, I don't think this is ever going to be a problem with a practical solution.
You're all kind of leading right into the next topic here, which is in this last section on management of indoor chemicals. You start with the hierarchy of controls, which, John, if you could pull that up real quick. It goes back to basic things we've known for many years that do work, as opposed to trying the latest, fanciest new technology out there. Bill, would you like to comment on this? And then I think what would be nice is we'll go to here and go into our roundup, and maybe we could do that real world discussion of how you did this at summer camp.
Sure. Well, I mean, just quickly, this is the NIOSH hierarchy that you'll find at their webpage, and it's an attempt to rank different controls in terms of their actual effectiveness as implemented. And clearly, elimination is the best way. Just get rid of a hazard entirely. Substitution, less desirable, but can be beneficial. Try to use something else that you perceive to be less hazardous, but even that's complex as described. Engineering controls, if you haven't stopped the hazard from getting into the susceptible individual, then we try to reduce exposure by various means. And we don't have many, it's just a handful: ventilation, filtration, chemical filtration, and inactivation or decomposition. And that can be fairly effective, but it's certainly not as good. Administrative controls, following rules and regulations. You can write great rules and regulations. The problem is people actually have to follow them. So that's why it's farther down. It's not that well-written rules couldn't be effective. It's just that in practice they aren't. And that's also the concern about PPE. And we've seen plenty of discussion of masks and their ability to reduce risk of infection, but they have to be the right masks. They have to be fitted properly, and a lot of people have to be wearing them. So that's what this tells us. And I think what goes with this that isn't in the report perhaps is the Swiss cheese model, that the more layers we have, the more holes through the pile of cheese we plug. So that's the other concept I think to keep in mind here.
All right, John, let's go to the roundup. The roundup is brought to you by April Air, providing healthy humidity, ventilation, and air purity solutions for new and existing homes. April Air, healthy air, healthy home at aprilaire.com. I've got a couple questions here that I don't know if we're going to have time to get into, but I did want to ask this one. When we purchase new furniture or other indoor materials, do we need to know the partition coefficient? And if yes, where can we find that? I mean, I assume it's not available, but anybody want to comment on that?
No, that's the role of standards and regulation. You should be buying products that are properly certified. Of course, lumber liquidators, I'll say no more, right? So the things have to be properly tested in certified labs and labeled, and that I think is how to make ourselves safer. Not everybody has to be a chemist.
I'll just add that furniture can be both a source and a sink. And so when you first buy it, it may have chemicals from manufacturing that will emit off of it. And then including if it has flame retardants, they may emit for decades. But it will also serve as a sink, and the materials will capture chemicals that are in the air and hold them for long periods of time. But there's so many different partition coefficients that just go into one single chemical furniture material. It's beyond what an average person would need or can do. In addition, we don't know a vast majority of partition coefficients. You try and do research in the field, and there's very, very few actual lab measured partition coefficients.
And that goes back, Bill, I'm glad you said what you did, because that's what I was thinking when you went through the hierarchy of controls. That's kind of what I was thinking about when I was looking at this question is, do we even have the information necessary, and how do we get it? Well, eventually either the manufacturers or the government's going to hopefully get us this information so we can better evaluate what we're doing in indoor environments. I think of carpet all the time. The manufacturers know very well what's in there and what it does, and they're working very hard to make it less problematic in many cases, but I don't know that information always gets to the research side or the regulators. Allison, you want to chime in on that?
No, I think it's been covered. As much as there are certifications available for things, it's a good thing to look for on products like furniture and other things.
All right. Well, let's do a real world example here. You were just recently at summer camp, and you did a presentation. We won't have time to go into the whole thing, but maybe you could quickly summarize what you did and kind of use the hierarchy of controls as an example, or kind of tie it back to the hierarchy of controls. But the main issue was concerned with COVID, I assume.
Sure. Yeah. And I gave a talk on infection control, what we know, don't know, what we need to know. And as we discussed this, it became apparent that we had an opportunity to actually demonstrate the kinds of recommendations ASHRAE, for example, has made in the classroom at the Regency where the Westford Day meetings are. And so Lou Harriman, who I'm sure everyone knows, arranged to make some visits to the site to look at the air handling units, check the outdoor airflow, and to see whether they could upgrade the filters from MERV 8 to MERV 13. And he also planned to build some Corsi Rosenthal boxes, which you can see there. And I know a gentleman who's with one of the main upper room UV providers, and he had recently been thinking about portable installations and was willing to provide one free of charge. And we also measured CO2 in the space. So what you see there is an upper room fixture on a stand in the corner. We had, I think, 4 of those spaced around this big room, and one of the Corsi Rosenthal boxes that Lou Harriman put together, and a CO2 monitor. So we put all of this stuff in place, and there are some pictures in the presentation of it. If you just kind of scroll through the parts that have yeah, so there's up on the roof, you can see Joe Steverick there on the right. They're checking out the air handling units. If we go on to the next one, here we're putting in filters, and a lot of the stuff that was learned from doing this wasn't just does it work or not, but it kind of highlighted how often things aren't the way we think they are, so it's important to check. So they got the filters the manufacturer recommended to put in their air handling unit, and they were the wrong size, and you can see one of the guys doing what they call filter origami there at the bottom, bending it enough to get it into the rack so it would fit. And then even more interesting than that, if you go to the next one, when they looked at the status of the outdoor air intakes, they found that for some reason they were 100% closed when the system was supposed to be in operating mode. So they measured the outdoor airflow and found it was a hard 0. And they had to do a field fix so we would have outdoor air for 450 people by taping open the dampers, which you can see there in the lower figure.
So here we are getting ready to have 400 or 500 people in a ballroom and no ventilation whatsoever.
Yeah. So if we go on here to the next one, let's keep going here. I've got just some data on the outdoor airflows that were available. The CR boxes, they were doing 1.1 equivalent air changes in total. A lesson there, you can get widely varying results depending on the fan you pick and the filters you pick. And I think we're a little bit surprised at the loss of flow from free flow through the fan, but we use them anyway, and they help mix the air, which could improve the UV performance. This was way under what AHAM would recommend for effective portable filtration in that room. You go to the next slide then. Here's what the classroom looked like with the UV fixtures in place. The blue light is not germicidal, but you do get a little bit of visible light. The fixture on the upper left is a so-called open fixture. You can use those in high ceiling rooms like this one because you don't have much risk of bouncing a lot of UV down into the occupied space. The other fixture that was used, just so people could see it, that's a typical louvered fixture, and it produces a much narrower beam. If you scroll up so we can see a little more of that bottom one, you see the louvered fixture is the one at the right, and look on the wall, you can see how narrow that beam is coming out of it. So if you have a low ceiling, you put them under it. Over on the far right is the
far right.
Yeah, just look on the wall next to the door. That's very narrow, and you can see that the open fixtures are throwing a lot of light up onto the ceiling, but no problem because the space was commissioned before it was used. So we went around with a radiometer and made sure that we were well below the exposure limits. Next figure shows the kind of distribution of UV light under the ceiling that you get from those fixtures. It's not quite the arrangement that we used. And you can, the top one is plan, and the bottom one is a section. You can see that it's a high level of irradiance, high and little low. So we can maybe get to the bottom line here. And yeah, so the next slide I think is the one. So I got the one with the chart on it. That one. Right. So the top figure is an attempt to show exposure reduction, assuming some undetermined number of infectious people in the room, and going from MERV 8 filter to MERV 13 with the outdoor air that they had, 28% reduction. The CR boxes in this case didn't add a lot because we didn't have enough flow, but then the estimated performance of the UV more than doubled the exposure reduction. And then I used a Wells-Riley calculator to try to figure out what the actual infection risk reduction would be. And I also threw in vaccination and 50% mask use. So if we assume 70% vaccinated people 4 infectors and nobody's wearing masks as the baseline. If we didn't change anything, but half of the people there were wearing N95 masks properly, that would result in a 55% reduction in exposure. If we take the masks off and then start with the engineering controls, the MERV-13 filters plus the CR box, relative reduction of 37% in infection risk. Add the UV and we get to 63%. If people are wearing their masks on top of that, it's 92%. So yeah, I think we need to do this kind of quantitative analysis to try to understand what is the incremental effectiveness of the controls that we're using. And you can transfer this kind of thinking from infection control to other kinds of exposure. You know, looking at dollies or some other appropriate measure of impact.
Fantastic. And you did that, wrap that up really quick and nicely done, Bill. And I like the way you tied it back. Before we go, let's get final thoughts. I don't know if anybody's had a chance to look through the questions. There were a couple I didn't get to. One was on advanced photocatalysis effect on chemical air contaminants in indoor spaces. First of all, what's advanced photocatalysis for our audience? Anybody want to jump on that one?
I don't know about advanced, but photocatalysis, you use light to activate a catalyst, and that produces usually reactive species that are supposed to decompose chemicals and disinfect microorganisms. There have been 2 ways of using that in closed devices, which have had some technical problems that are described in chapter 5. And also some of these reactive species air cleaners that are putting stuff into the room are using photocatalysis to produce reactive species. And there are also surfaces that are photocatalytic. So a number of ways of doing it. I think the problems are the same for all of them. How well do they work? How well do they work over time? And is there incomplete decomposition of chemicals that produces things that are worse than we were trying to control in the first place? And Dustin, I'm sure, has some good add-ons to that analysis.
Dustin? All right, let's go around. Go ahead.
No,
I just want to go around the horn and get final thoughts on what we've learned from this project and what it means for those of us that manage and inspect for indoor environmental issues. Let's start, Allison. Let's start with you.
Sure. So I think when we EPA and the other sponsors of the report really started to think about this report, one of our goals was to identify some of the important pollutants of concern, some of the drivers of indoor chemistry, and ways to mitigate and reduce their impacts. And we were especially interested in exposure disparities and disproportionate impacts for vulnerable communities and susceptible populations, because everyone spends a lot of time in indoor environments, and practically anyone is impacted by this issue. And so I think this report lays a great foundation for us to continue to raise awareness of indoor chemistry through our technical assistance and public outreach in EPA, and we are going to find this invaluable as we think about research plans for the future. And I think there's a lot to take away for the restoration community as well. And we've talked about some of those things today in terms of thinking about the different partitioning impacts on different approaches to remediation. So I definitely encourage folks to go and check out the report. I dropped a link in the chat for you to go download a copy if you feel so inclined.
I got a quick follow-up, Allison. Did this start before or after COVID?
Actually started before, yeah.
Okay, I'm just curious, has the advent of COVID changed the thoughts at all on how we look at indoor environments? So I guess it's probably increased at least, people's interest.
Yes, definitely. It's definitely brought a lot more attention to indoor environments. We have a program that works with indoor air quality in schools, and that's, been a big portion of the work with schools, as well as all of our other work as well. We put up our webpage on indoor air and coronavirus, and there's a lot of great information there about ventilation and filtration strategies to help reduce airborne transmission. So I think that we've made a lot of progress in getting people to think about their indoor environments, and it's unfortunate that this is the way it had to happen, but I hope that we can build off of that momentum going forward.
All right, Dr. Dustin Poppendieck, nice to have you here. Any final thoughts for our listeners?
Yeah, building on what Allison said, we spend 90% of our time indoors. We all are exposed indoors. We need to really understand, and COVID was a silver lining that people are now thinking about their indoor environments, not just from a COVID perspective, but just from a health perspective in general. But I think as we start thinking about that as a general population, the report really emphasizes that we really don't know a lot about our indoor environments, despite the fact that we spend so much time in them. And we don't really understand what's happening and what things are good and what things are bad. Well, we know some things are clearly bad, but we don't understand the extent of some of our problems, whether they're insignificant, we really don't need to worry about it, or they may be significant because we just haven't looked at it close enough. And so I think the report really highlights that there's a lot of unknowns, and we just don't have all the answers, and we need to spend some time figuring those answers out and spend some resources figuring those answers out. But in addition, communicate the results of those findings, and make sure that we're communicating them to the populations, as Allison was pointing out, underserved populations and populations that have very disparate air quality, both indoors and out.
And I think you're kind of building a baseline of things that, and making recommendations for what we need to look at in the future. I hope we can have more practitioners involved in helping with what we need to learn about for the future. And Dr. B.Bahnfleth, always great to have you here. I just want to get your final thoughts. And I did have one more text. So the implication was 100% mask use would eliminate exposure. N95, let's at least, this is a text question from a listener, not from me.
You shouldn't draw that conclusion, right? It's like if I put two 75% efficient filters in series, I don't get 150% removal of the contaminants. It's asymptotic. You get diminishing returns as you go farther and farther.
And that doesn't even include the other issues with, like, will we understand each other speaking and so forth.
What I would say, on
people wearing an N95.
Yeah, what I would say is a closing comment, just to maybe cast a ray of hope on what Dustin just said, is that there's an awful lot that we don't know, and these national academies committees, that's their job, is to figure out what we don't know and to chart a way to fill in those gaps. But we do know a lot of stuff, and I think we have to recognize that we have the ability to make indoor air quality, indoor environmental quality better with what we know, if people actually know what we already know. And I would say, as a mechanical engineer, in the last chemistry class I had was a sophomore in college. Those of us who are mainly on the side of how should buildings be designed and operated could stand to know a lot more about the things we've been discussing today than they normally do. And I think that's a big part of what we need to do to improve indoor air quality is a workforce that is more sensitive to these issues and knows how to deal with them.
Yeah, just reading through, especially chapter 5, and I would urge people, go ahead and download the report and read chapter 5. I know the first 4 might be a little more than what we typically get into, but it's very, very concise and describes how to manage these issues very well. One of the things that caught my attention was the skin thing, and it said skin oil oxidation chemistry in indoor environments. It kind of opened my eyes when I read that paragraph. It's only a paragraph, but I read that paragraph and it kind of made me think, we deal with skin much, much more than we realize. We may be in there removing mold, or we may be removing soot or cleaning up after a water damage, but we're dealing with skin all the time. And I don't think we always appreciate that as much as maybe we should, and how important it is. So that's just kind of my final thoughts on the document and how it kind of opened my eyes. And I want to thank our guests this week, Dr. Dustin Poppendieck, Dr. B.Bahnfleth, and Allison Savage. Thanks so much. And always enjoy getting together with you and look forward to talking again.
Yeah, thanks a lot. Great to be here.
Thanks.
Thank you.
All right. This is Radio Joe Hughes saying thanks again to our guests, to my co-host, the Z-Man, Cliff Zlotnick. John, you got to have faith at the controls. Most importantly, our audience and our sponsors. We'll be back next week. By the way, next week we've got a restoration focused show. Tom Peter will be here with us. Many of you know Tom. He's been on the show several times in the past. He's also a certified industrial hygienist. And we're going to have one of First On Site's remediation folks in. We're going to talk a lot about remediation and some current issues in remediation. So come back and join us next Friday at noon for the next episode of IAQ Radio Plus.
For IAQ Radio, I'm Spike Reel saying thanks for listening.